Lab 2 is on falling motion. I'll be dropping a beanie from rest and then I will model it with only gravity, then I will model it with gravity and drag. So what's known is the mass of the beanie, which is 0.0567. We know the initial velocity is 0, and we know the gravity force vector is 0, negative mg comma 0, where g is 9.8 meters per second. Also, we know the y dimension of the whiteboard is 58.5 centimeters, and we can convert this. And this lab is important to see the effects drag can have on precision when modeling falling motion. So first, in Tracker, I added a calibration stick with the length of the whiteboard, and I hit it. Then I added an axis. I hit the axis, and I tracked the new point mass. I tracked the points, and I inserted the mass. And from that, I was given the graph, a position versus time graph. I was able to see that the position is decreasing, and the tangent line slope is becoming more negative, meaning that the velocity is increasing in the negative y direction. So then I model it using Newton's second law, which states the force applied on an object is dependent on the mass and the acceleration of the object. From this, I use the velocity update formula, which is the final velocity equals the initial velocity plus the net force over mass times the change in time. Also, I use the position update formula, which is the final position equals the initial position plus the average velocity times the change in time. And for this lab, we won't be using constant forces, so we'll be using the average force equals the final force. So for GlowScript, first I put in the mass of the ball, then I changed the initial position vector, and then I changed the gravity force vector. Then for the net force, I put just gravity because in this model we're only using gravity as the force on it. Also, I used the Newton's second law velocity update and the position update. Also, for the arrows, I used the position of the arrow would just be the ball position, and the axis would just be the gravity vector. So in GlowScript, then the model came out like this, but one bad thing about it was that it landed way under the origin, when in real life it just landed at the origin. So we compare it with the other graph, we see that the position is decreasing in both, and the tangent line slope is becoming more negative, meaning the velocity for both is increasing in the negative y direction. But we see that Model 1's final position is negative, so that means the force of gravity is not the only force acting on the system. So if we go back to the first model, we can just add in that the net force equals the gravitational force plus the drag force. We need to see what is our drag. So drag points in the opposite direction as gravity force. So it's pointing up or the positive y direction, and it's going to be proportional to the speed of the ball squared. Since we cannot square a vector, we're lucky in this case because the only non-zero entry in the vector is the y component, so we can use the y component of velocity to be equal to the magnitude of velocity in this case. So our drag is going to be b times the ball velocity y component squared. So to model this in GlowScript, we start with model 1 and we just change b to be 0.03, which is through guess and check we found b. Also, we create force of drag vector to be 0, 0, 0. And then inside the loop, we make velocity squared. Also, we create the drag force vector. And we update the net force to be gravity force plus the force of drag. And then for the arrows, we just update them the same way as we did for gravity. So we can see that this model slowly increases the force upwards, which is the drag. So it slows down the acceleration, and it stops right at the origin. So when we compare this to the tracker model, we can see it's much more similar, and the differences we see can be accounted to the blurriness in the video in tracker. And one way to fix this would probably be to shoot in a higher frame rate. So our model with drag is more accurate of real life systems. So what does this mean for terminal velocity? Well, terminal velocity is when drag force equals force gravity, meaning that the net force is 0 and the velocity does not change. So for Model 1, there's no drag, so it's infinite acceleration, so there's no terminal velocity. But for Model 2, there is the force of drag, and when this equals the force of gravity, then it will reach the terminal velocity. And if we put this in GlowScript and increase the time, we can see that the terminal velocity is negative 4.304. So what if the initial velocity was not zero? Well, there's three cases when the initial velocity is the same as the terminal velocity, the initial velocity is greater, and the initial velocity is less than terminal. Well, for all of them, the force of drag updates in the model, and it creates it so the terminal velocity is the same pretty much for all three. And if I model this for the first one, for case one, it's the same. For case two, it becomes the same right there where it becomes horizontal. And for case three, it's also the same when it becomes horizontal.